Vanakkam. Welcome to this course on biomedical instrumentation. We have been looking at electrode theory. In this video, we will look at a broad summary of electrodes theory. So, what is of interest for us? We are interested in biopotentials because our cells are biological batteries. Excitable cells are biological batteries, those that maintain a steady potential difference across the membrane. We are interested in measuring these potentials and their variations across time and space. These are the signals of interest. Biopotentials are the signals of interest. And we looked at in the previous set of videos how action potentials are generated. Action potentials are these dynamic signals in excitable cells. These are the dynamic signals of interest that cause these biopotentials. And then we looked at what is an electrode. And electrodes are essentially the transducers that convert ionic currents to electronic currents. Important to note is that ionic currents, neural signals, do not travel at the speed of light. Maximum neural communication, maximum speed is about 120 meters per second. Verify this. And one major factor that affects signal quality is impedance. Especially when you are interested in measuring from the surface, you are interested in matching impedance, minimizing the impedance by, for example, abrading the skin, abrading the stratum corneum and applying alcohol, for example, impedance. Then another major factor that affects signal quality is polarization, right? Stability and performance is affected by polarization, and that means what particular electrode that you use for recording. The choice depends on the application and the frequencies of interest, for example, and whether there will be movement artifacts, and these movement artifacts will constitute a major challenge in processing these signals, for example. Practical stable recording electrodes we have seen in the previous videos are these silver chloride electrodes. These are practical stable recording electrodes. And if you are interested in the surface electrodes, skin interface is the final link to the body. So, you place the electrode on the surface of the skin and apply a gel, for example. Of course, there are other challenges, we already said, abrading this, shaving, abrading, apply alcohol, apply gel, and then just to minimize skin impedance. The other approach, an invasive approach, is to use internal electrodes. These are invasive but provides better resolutions and better measurements where needed, but then it comes with the baggage of being invasive. So, you get better quality signal, but then they are invasive. So, you need to make a choice as to which ones. Micro electrodes are really tiny. They can provide very high quality and high spatial resolution based recordings, but then it comes with its own challenges. What are the challenges? We already saw what the challenges are when we discuss microelectrodes. Electrode arrays essentially provide high spatial resolution and but usually involve high technology because they involve microelectronic fabrication techniques as the technology. But remember that more electrodes does not always mean better. High density does not always mean high resolution. That is not true because volume conduction effects still persist. We will discuss volume conduction in a little bit. Critically, it is important for us to recognize that each component affects the overall performance of the system. We need to learn that systems thinking, that from the skin to the recording system, each component in that lead wire, whether you are soldering or not, whether you are welding, are the metal and the lead wire of the same type of metal or different types of metal, all these things matters. So, each component affects the overall performance of the system. There are trade-offs. There is no such thing as a perfect solution. The solution that you want depends on the particular application of interest. So, there are different problems different solutions that exist. Importantly, physics, also the chemistry and the biology. I am saying physics essentially to mean the broad fundamental science. Physics matters, fundamental understanding of the principles of how this works can inform the appropriate choice of recording, the modality of recording in a big way. Also, clinical context matters, because patients may bring in, specific patients may bring in additional complexities. For example, is the person elderly, the skin type is different. Is the person diabetic, because altered skin properties exist in diabetes. Is it a neonate, is it a baby, then skin can be very sensitive in this. And the whole field is evolving, the whole field is advancing every single day. It is an evolving field, it is an evolving science. So, what I tell today may not be appropriate few years from now. So, these are all some of the things to keep in mind when you choose an electrode. So, what does the future look like? Essentially, wireless wearable sensors for continuous monitoring and patient specific information that you are going to record for a long time and get information that is specific to that patient, and brain computer interfaces that use, for example, multi arrays, many arrays, that direct neural controller, for example, prosthetic systems, maybe a prosthetic arm, or for example, prosthetic speech system, etc., for example, or therapeutic stimulation devices, those that use stimulation, bioelectronic devices of the type, for example, deep brain stimulation in Parkinson's disease patients, for example. Critically, these electrodes and the advancements in the electrode theory can help in providing personalized, tailored therapy, tailored approach to medicine. Right. Critically, the next step will be a step where biological components and electronic components getting merged in some form, that biocompatibility and those challenges are addressed in a very big way. Right. Wanted to discuss about volume conductor effects. What happens, this is critical, because in excitable cells what happens is, let us assume that this is a patch of muscle of interest, and I am interested in measuring the activity, electrical activity of this muscle. Let us say a wave of action potential is traveling through this muscle, like this, in this direction, right. Now, if I place an electrode here, because the muscle is an excitable cell, if I place an electrode here and an electrode here, the activity that is happening here will also partially affect the activity that is happening here, because of the conductive nature, because the muscle is an excitable cell, right. On top of that, it is possible that this part of the muscle itself is having its own conduction. So, when what I am measuring from this point is essentially a combination of neighborhood activity plus own activity. But then I do not have an idea of what I am measuring, I am just measuring an activity, I am measuring this sum, this is what is the measured activity. Measured activity is the neighborhood activity plus the own activity. I do not know what is the own activity. I am interested in knowing the own activity, but I have no way of knowing it. This is a common problem. So, these electrode arrays and improved spatial resolution to some extent mitigate this problem, but does not completely address this problem. The problem continues to exist. In surface recording, this is a huge problem. In fine wire, in needle and electrode arrays, this is lesser of a problem, but it is still a problem. Now, how do you address this? One is to understand, one is to perform mathematical modeling, forward plus inverse modeling. Forward, what is a forward model? Having an idea of model of propagation propagation of bioelectricity in that particular tissue. That is the forward model. Inverse model is, given that I have recorded this and I know that this is the model of propagation of bioelectricity in this particular tissue sample of interest, what would be the own activity? To some extent, this forward model essentially estimates this neighborhood activity. The inverse model, from the measured activity and the forward model, tries to estimate the own that particular cell or that particular region's activity. So, essentially you are going to have the challenge of mathematical modeling or a combination of forward and inverse models to address this volume conductor problem. It is a huge challenge that continues to exist. With this, we come to the end of this video and to the end of electrode theory. Do look at these details of the volume conductor problem, because this is a huge problem in many surface recording modalities. Please do look at it for your own interest and enthusiasm. I am not having the time to discuss this in detail, but I will mention this from time to time in future recordings, future videos. So, with this we come to the end of this video and to the end of electrode theory. Thank you very much for your attention.